We usually think of chemical reactions as a one-way street, right? Reactants go in, products come out. End of story? But what if I told you that some of the most important reactions in the entire world, well, they never actually finish? Today, we're jumping headfirst into the mystery of the unfinished reaction.
Okay, let's dive into this with a massive real-world example, making ammonia. This is the process that literally feeds billions of people. You take nitrogen and hydrogen, you expect them to turn completely into ammonia, but they don't. They never do. The reaction just kind of stalls, leaving you with this mix of the stuff you started with and the stuff you were trying to make. So why? Why doesn't it just go all the way? That is the exact puzzle we are solving today.
So, to crack this case, our first clue is to understand what's really going on when these reactions stop. See, it's not that they've run out of gas, they've actually reached something way more fascinating. They've achieved a state of equilibrium.
So what on earth is equilibrium? Well, at its core, it's just a state of balance. Picture a seesaw with two people who weigh exactly the same. It's perfectly level, right? It's not moving up or down. In chemistry, it's the same idea. It's that moment when all the measurable things, like how much stuff is in there, the pressure, even the color, they all just stop changing. They lock in and stay constant. Let's actually watch this happen with some simple molecules. We start with a beaker full of just reactant A. As the reaction kicks off, A starts turning into product B, and you can see the mix changing. It keeps going until, bam, it hits a very specific ratio. In this case, it's 3 A's and 3 B's. And once it hits that sweet spot, the amounts don't change anymore. No matter how long we wait, the net change is 0. That's it. That's the equilibrium state. But here is the single most important idea to get your head around. The reaction hasn't actually stopped. This is the big misconception. It's in what we call a dynamic balance. Molecule A is still turning into B, but at the very same time, B is turning right back into A. So at equilibrium, the speed, or the rate, of the forward reaction, that's A becoming B, is exactly equal to the speed of the reverse reaction, B becoming A. It's kind of like trying to walk down an escalator that's going up. If you walk down at the exact same speed the escalator is moving up, you're constantly moving, but you're not actually going anywhere. You're in a perfect dynamic balance. Okay, so we figured out what equilibrium is, but we still don't know the big one. Why does it happen? Why does nature want this balance instead of just, finishing the job? The answer, it turns out, is a fundamental battle at the very heart of the universe. And this brings us right back to our central puzzle. We learn in thermodynamics that systems love to be at their lowest energy state. So if the products are more stable, if they have less energy than the reactants, shouldn't the reaction just run downhill until every last reactant is gone? What could possibly be stopping it?
And here is the answer. It all comes down to a cosmic tug-of-war between two competing laws of the universe. On one side, you have the drive for lower energy. Everything wants to settle down into its most stable state, kind of like a ball rolling to the bottom of a hill. But on the other side, you have an equally powerful force. The universe absolutely loves chaos. It always pushes towards maximum messiness, or what scientists call entropy.
Think about it this way. A box with only blue marbles is pretty orderly, right? But a box with a mix of blue and red marbles all jumbled up, that's way more disordered. It's messier, and that mixed up state has higher entropy. Nature, for whatever reason, loves that messiness. So this powerful drive for messiness actually changes the whole energy landscape. Instead of a simple, smooth slide down to 100% products, the entropy that comes from mixing things up actually carves out a little energy valley somewhere in the middle. The reaction slides down the hill, but it gets stuck at the bottom of this valley, which is a perfect mix of reactants and products. That spot right there is the true lowest energy point for the whole system. So the big reveal is this. Equilibrium isn't some kind of failed reaction. It's the ultimate cosmic compromise. It's the perfect balance point that satisfies both the drive to be stable and low energy and the drive to be as messy and disordered as possible. Mystery solved. All right, so we've cracked the why. Now let's explore how this powerful principle of balance actually shows up in the real world. Turns out we can classify equilibrium in a few pretty straightforward ways.
First, we can basically sort it into two main buckets. You've got physical equilibrium. This is all about changes in physical state. Think of an ice cube floating in water at exactly 0 degrees Celsius. It's melting and freezing at the exact same rate. Then, of course, you have chemical equilibrium, which is what we've been talking about, that perfect balance inside a chemical reaction itself.
We can also slice it up another way, by phase. If everything in the reaction is in the same state, like they're all gases, we call that a homogeneous equilibrium. Easy enough. But if the components are in different states, say a solid breaking down to form another solid and a gas, we call that a heterogeneous equilibrium. Simple as that.
So, we know equilibrium is a balance. But how do we describe that balance with numbers? How do we know if a reaction likes to have more products or more reactants? For that, we need the final piece of our puzzle, a little something called the equilibrium constant.
The logic here is actually really elegant. Check this out. We already established that at equilibrium, the forward rate equals the reverse rate. So if we just write out the math for those rates and set them equal to each other, we can do a little rearranging. And what we end up with is this new constant, which we call K. And K is simply equal to the concentration of the products divided by the concentration of the reactants. It's a beautiful piece of logic. Now this constant, K, comes in two main flavors. We use Kc when we're talking about molar concentrations, usually for stuff dissolved in a solution. But for reactions that involve gases, it's often a lot easier to use Kp, which is based on the partial pressures of those gases. And what's really convenient is that these two worlds, concentration and pressure, are connected. There's a pretty simple formula that acts as a bridge, letting you convert between Kp and Kc whenever you need to. It's incredibly handy for chemists working on the same reaction under different kinds of conditions.
Okay, one last really important rule. Remember heterogeneous equilibrium with the different phases? Well, when you write out the expression for K, you actually leave out pure solids and pure liquids. Why? Well, because their concentration is basically constant. It doesn't change during the reaction. So for a reaction like limestone decomposing, the equilibrium constant Kp is just the pressure of the carbon dioxide gas. That's it. Everything else gets ignored.
So we've seen that a chemical reaction is so much more than a race to a finish line. It's this incredibly sophisticated search for the perfect balance between stability and chaos. And that leaves us with a much bigger question, doesn't it? If the fundamental building blocks of matter are driven by this constant search for balance, what other complex systems, from our planet's climate to our own bodies, are also secretly being governed by this exact same principle?